So this topic is called U substitution. And I don't know who decided that the letter we were going to use to substitute was going to be U, but that's like the official name. Like in the textbook, it's called U substitution. Like you can Google U substitution and that is what it is. That's what they just decided, the letter that everyone decided that they were going to use. This is integration, like finding an antiderivative when you can't just write the answer. Like all the ones we did last class, I was like, oh, just add 1 to the power and then divide by that. Or like just come up with a function where if you did the derivative, you would get this. This is if the problem is more difficult than that. So if you look at it and you're like, oh, I can't just write the answer, that's when you need to use substitution. Because I always get asked like, hey, Ms. Cole, how do you know when you need this? If you can't just write the answer, you need a different method. All right, so here's the first one that we're going to look at. So when you look at that, that is a bit of a mess. And you're like, oh, well, I can't just like say the answer. So you need, a different method. And I'm sorry, that'll brighten back up. So what a U substitution does is it allows you to do a chain rule in reverse. You know how when you do a chain rule, when you do a derivative, you tack on, like you chain on the derivative of the guts of the problem, like the inside stuff? We're going to do that in reverse. So what you want to do is let U equal, and we're substituting out for U. You want to let U equal the inside stuff, or like the guts of the problem, the part that's inside the function. Or when in doubt, if you like can't figure out what to let it equal the thing with the highest power or the denominator. If you're just not sure, those are 2 other things that you can get. But here's the deal. If you pick the wrong thing, it just won't work out. And you'll be like, oh, let me pick something else. I taught this a couple of years ago and someone goes, oh, so if I just keep on trying, I'll eventually get the right answer. And I was like, yeah. Okay, so if you pick the wrong thing, you can always just pick something else. For this one, we're going to let U equal this part right here. It's inside of the exponential function. So that's like the guts of the problem. So the 2x squared plus 4x minus 9. And then you take the derivative of that. So it's du dx. This is the only problem I'm going to write out this step on. After this, we will always skip this step. You'll see why in a second. What is that derivative going to be? We're going to do the derivative of this. 4x plus 4. And what you want to do is multiply over the dx. So I'm always going to skip that. We'll just write du equals and then take the derivative and put a dx. Now here's where it has to match what's in the problem. So you have to go and find that. Now you can adjust it by multiplying or dividing by something, but the variable part needs to be there. So do you see that anywhere in the problem, or could we adjust for it to like fix it so it matches? Go ahead. Perfect, right there. Hey, Ms. Cole, what if it doesn't match? That means you picked the wrong thing for you and you would just go back and pick something else, right? So divided by 4, I'm going to just put a 1/4 out front. Again, that's a personal preference thing. Some people like to put du over 4, however you want to do it, right? We divide all this by 4, we get x plus 1 dx. This is the part that I always just tell everybody to highlight. You don't have to, or were you going to add something in there? No, oh, okay. I like to highlight the part that matches. So we're substituting for this x plus 1 dx. And so whatever you did not highlight is still there. So it helps you see what you already took care of. The part I highlighted, we already took care of. This 1/4 we're going to put out front of the integral. Du goes at the end. So in place of the highlighted stuff, we put 1/4 du. What's still there is e to all of this, but what are we replacing all of that with? U, it's e to the u. The idea is you take something that looks really complicated and make it look really simple. What happens with these is it gets to the point sometimes where it's almost so simple that people forget to do an antiderivative. This one you almost can't forget because the antiderivative of e to the u is e to the u. So it's 1/4 e to the u plus c. And then the last step, you're going to plug this stuff back in for u. So it's 1/4 e to the power of all of that plus c. essentially, that is it. We're just going to do a bunch of problems. And then I have to go over all the trig, and there's going to be more stuff, more fun things for you guys to memorize. Okay. But in essence, that's it. We're just going to practice that a bunch of times. So here's the second one we're going to do. Those of you that saw this last year, is that like coming back to you sort of? It's like doing a puzzle. I know that they're very cut and dry and boring, but a lot of people end up actually liking them because it's very much like doing a puzzle, and that like appeals to some people, like, oh, all the parts are going to fit in there. These, yeah, you can churn them out once you get good at them. All right, but it's a drill and practice thing. All right, you want to let u equal the guts of the problem, like the inside stuff. So what would we let u equal for this one? Good, like the stuff that's inside. Again, if you struggle with that, it just won't work out, and you'll be like, oh, I'll pick something else. So if your perseverance is there, you'll always get through it. So du equals, that derivative would be 3x squared. Perfect. And yeah, so I skipped that du dx step, just put the dx at the end. Now you have to find that. It will be there. If not, like I'm not going to give you an undoable problem, right? How will we adjust this to make it match what's in the problem? Multiply by 4, perfect. So 4 du equals 12x squared dx. And again, I like to highlight the part that we're substituting. It's the 12x squared dx. Because then you can go, oh, that's the part I took care of. Whatever you didn't highlight is still there. Okay. So in place of that highlighted stuff, we're putting 4 du. You want to put 4 out front and then du at the end. And then what's still there is square root of u. Don't write square root of u. Write u to the what power? Perfect. Good. And then this is like fun with fractions here. You want to add 1 to the power. Now you would never see u to the power 1 1/2. It would be 3/2. So out front, you're going to put 2/3. The 4 is still there, and then plus c at the end. So what would that fraction out front be if you combine those together? Good, that would be 8/3. And then we have to substitute back in for u. U is this x cubed plus 1. The rule of thumb is you should write your answer in the same format the question was given. So if this is written with a square root, we should write ours with a square root. So it's going to be square root of this x cubed plus 1 to the 3rd. And then plus c. This one, I guess technically you could multiply all this together and then just do a regular antiderivative, but we're practicing u substitution, so let's do the problem that way. There's not really a clear cut like insides of the problem, so you want to go with the thing with the highest power. So you would let u equal the x to the 6th plus 2x squared. And so du would equal what? Or are you all just busy doing the problem? What's this derivative going to be, guys? This plus 4x. All right. Just like to know that you're with me, so I'm not just like lecturing at you. All right. What are we going to adjust that by to make it match what's in the problem? 1/2. Yeah. Divide by 2. So in place of the 3x to the 5th plus 2x dx, we're going to put 1/2 du. You want to put the 1/2 at the front, the du at the end. And then this is one of those ones that almost becomes like so simple that it confuses people. What's left? u. Like this was what we let equal u, so that's it. And then people forget to actually do the calculus. Like we haven't done any calculus yet. Here's the antiderivative. Well, I guess we did do a derivative there. What would be your antiderivative of just u? Good, 1/2 u squared. Just don't forget to do that. And then we have another 1/2 that's out front, and then plus c at the end. So that would be 1/4 u squared. U is this stuff. It sounds like I don't know how to speak when I teach this. U is this. All right, all of that squared plus c. This one has trig in it, but we're not going to actually do any trig. Like there's no unit circle in this or anything. So, yeah, I see trig functions there, but we're not going to actually do any trig. What would you let u equal for this one? Tangent of x plus 5. Yeah. When in doubt, you want to pick the denominator. Like if you can't find the insides of it, like the guts of the problem or the thing with the highest power, when you're just like totally guessing, pick the denominator. Also, what is this derivative going to be? Yeah, and you can like almost use the problem is almost helpful, if that makes sense, like because it's going to have to match. And we don't even need to adjust that. So there's no adjustment number. We're going to replace the secant squared of x dx. And there's no number that goes out front. You'll just put du at the end. Like I said, we didn't have to adjust that. And then what's still there? 1/u. Perfect. So that antiderivative, ln of u plus c, and then you put this stuff back in for u. So your final answer is ln of tangent of x plus 5 plus c. And absolute value that. Again, you can't ln a negative value. I don't say the absolute value every time because it's a little bit of a mouthful, but it is there. All right, I'm going to change it up on us just a little bit. What did I make different about that one? It's a definite integral, so you have boundaries. So we will not put a plus c. Instead, what are we going to do? Yeah, like actually value. It's fundamental theory of calculus. You're going to do upper boundary minus lower boundary, and you'll get like a numeric result. Remember when you do that, what are you actually finding? Like the result represents perfect area under the curve. Okay, because people will start to churn these out and then forget what they're actually doing. All right, so we would let u equal what? Good, the stuff in the parentheses, like the insides of it. And then that derivative is 4x dx, which, hallelujah, we don't even need to adjust anything there. It's just going to match up. So that's nice. And so the part that is highlighted is taking care of what is still there, u squared. Now here's the part where you have to adjust the boundaries. It's not difficult, but you have to do it. You're going to take the 0 and the 1, plug them in right here where I'm pointing for x, and see what you get for u. They are x numbers. You have to change them into u numbers. Does that make sense? We're adjusting them. So if you take 0 and plug it in for x, what do you get? That will be 1. If you take 1 and plug it in for x, what do you get? 3. Again, it's not hard, but you have to do it. You can't mix and match your variables. You have to like make a complete change to u variables. And then remember to do the antiderivative. This would be 1/3 u cubed. Evaluate from 1 to 3, and we're going to do upper boundary minus lower boundary. You don't have to plug this back in because we adjusted the boundaries to be U values. So you get to skip that step. Go ahead. Then you don't change these. Let me finish this and I'll work it out that way as well. And you can see them side by side and then we'll have a brief chat about it. You've never changed the boundaries? Okay, let me finish this problem. I'll show you it the other way and we will do another one, but let me finish the problem. Okay, so we're gonna do upper boundary minus lower boundary. If you plug in 3 cubed is 27, a third of that is 9. And then minus a third. Okay, I'm gonna work it out the way that they're all saying here. So we're gonna work this out the other way. So you would have, instead of changing the boundaries, what I would do is maybe just like leave them off for a second. So you would get to this step, you would get 1/3 U cubed, but you would put this back in. Are you still with me? Is this what you guys did last time? All right, and you would not change the boundaries. You would just leave them alone. And then you would do upper boundary minus lower boundary. We're gonna get the exact same thing. If you plug in 1, this would be 3 cubed is 27, a third of that is 9. If you plug in 0, this is 1 cubed, which is 1 times a third is a third. Do you see how you get the same thing both ways? Okay, so I don't really care which way you do it. I think this is more work. But all I'm going to tell you is this. On the multiple choice part of the exam, they will force you to do it this way. Because they will say, let U equal blah, blah, blah. Which of the following options is the substitution? And the answer will look like this. And you have to know how to change the boundaries. So you can do this for me if you like. This will be on the AP exam and you cannot avoid it. On when you took the exam? Okay, well, here, you know what, let's do another one. I'll work it out both ways, but you do have to know how to change the boundaries. Let me see, we'll do one more and then we'll do a break. Yeah, because they'll force you to. It'll be like, and I'm sure there's one in the homework for next time. They'll be like, let U equal blah, blah, blah. And then you don't have to actually work the problem the whole way out. You'll just do the substitution. And it'll be which one of these problems matches that. And you have to change the boundaries. Like they'll force you to do it. So what would be let U equal here? Good. The thing with the highest power, or when in doubt, pick the denominator. So that derivative is 3x squared dx. And we would have to adjust by multiplying by what? 2. So 2 du equals 6x squared dx. And so this is the part we're substituting for. So 2 goes out front, du goes at the end. We highlighted the part, we took care of that. What's left? One over u. And then we're going to adjust the boundaries. All you're going to do is take the 0 and the 3, plug them in right here for x, see what you get for u. So if you plug in 0, you get 4. And if you plug in 3, that'll be 27 plus 4, 31. So like on the AP exam, this would be the answer. They would be like, and there would be other choices, and they would be like, which one of these matches this problem? All right, so what would this antiderivative be? ln of u such that 4 to 31. I'm going to work it out this way first, and then I'll do it the other way. Again, I don't care, but you have to know how to do this. Right? So upper boundary minus lower boundary, it would be 2 ln of 31 minus 2 ln of 4, whatever that is. So if you wanted to do it the other way, you would get here and just like leave off the boundaries for a second, like just leave them off for a second, and you would get 2 ln of, and then you would plug this back in. See, that's why I think this is kind of like more work, but you don't have to change the boundaries. So there's that. you would leave them 0 to 3. And then when you do upper boundary minus lower boundary, you're going to get the exact same thing. So it'd be 27 plus 4 would be 31. 2 ln of 31 minus 2 ln of 4. So same thing either way. So once you get that's a really good question. Once you get a numeric value, you can drop it. As long as it's a variable, it has to be there. Because technically, like if we plug in 31, the absolute value of 31 just is 31. So that's why it's okay to drop it there. But as long as you have a variable, you have to keep it.